Welcome to part 2 of hardware representation and 3D math. Let's talk about bitwise operators. Now, bitwise operator, what do I mean? I just mean the math operators that work on bit by bit of a binary value. Let's get to it. First one, the bitwise OR. The bitwise OR is the single vertical line. Many of you know this, but some of you, I often encounter, some of you have never really seen this or haven't seen it very often. When we do an if statement, all right, you can combine two if statements. You say if x or y with a double vertical line. And that doesn't mean bitwise, that means logical. It means if this is true or that is true, then they're both, then together it's true. The bitwise version is to treat a number bit by bit and do an OR on every individual bit. Let's go straight to the example. Let's have these two binary numbers and we're going to OR them with a single vertical line, means bitwise OR. So 0 or 0, that's 0. 0 or 0 is 0. 0 or 0 is 0. 1 or 1 is 1. So true or true, that's true. 0 or 1 is also true. So false or true. So we think of this as like if false or true, well that's true. So that's a 1. 0 or 1 is 1. 1 or 0 is 1. 0 or 1 is 1. So there's our answer, the bitwise OR operator. Now, where we see this most commonly is when we're using an integer to represent a series of Boolean values, and rather than doing the colon, like bool b colon 1, instead of doing that, we've just created an integer, in this case an 8-bit integer, that holds 8 Boolean values individually. And we'll call that like a flags. We'll call that integer flags or something like that. And you'll see it very commonly in the DirectX stuff, but all over the place as a flag set. So for example, we'll do, usually use defines or enums or something to indicate, give us a symbolic name for each of the bits. So the least significant bit here, for example, is called draw debug line. And then the next bit, this is the 2's bit, is use fast rendering, and we define that to be the value 2. And then I've got one enable sound is the next bit. So these 3 bits here, all apparently set to false, are, they have these meanings. And how you would use the OR to combine them is simply, say I want use fast rendering and I want enable sound. So I OR those 2 bits together and I'll get the combined flag. Next up, bitwise shift. I think we may have already seen this one some in the class, but I don't remember. We shuffle the order of the lectures every once in a while, so maybe we haven't covered this yet. The bitwise shift operator just says to shift the binary bits to the right or to the left. Shifting to the left, let's do that first. And the number over here on the right-hand side says how many bits we're shifting. So if I shift it 1 bit to the left, then this 1 goes to there, the 0 goes to there, the 1 goes over, etc. Everything just goes over by 1 bit. The 0, the most significant bit, whatever it was, boop, it falls off the end of the register, and that'll go into the overflow or carry flags. But it's not going to fit in an 8-bit register, so that one's going to get struck. What about this least significant bit? The least significant bit comes in from the less than least significant bit, and we'll always assume that the less than least bit is 0. Right? So if you take 0 and you shift it left by 1, it's still 0. Okay. Shifting to the right. Shifting to the right, we do the same thing, only we go to the right. So this least significant bit, this makes a lot of sense. The least significant bit just gets truncated, just gets thrown away. and yeah, you thrown into the carry flag. For what that's worth, you can, if you're writing assembly, you can use that, but we're not gonna. What about this most significant bit? Now, the most significant bit on a right shift is interesting. If you have said that this is a signed value, if you've told C++ that this is a signed 8-bit integer, then when you shift right, it will fill from the left-hand side, from the most significant bit, it will fill in with your starting value. So if it was a negative number and you shift right, it will still be a negative number. It will fill it with ones. But if it was a positive number, it would have a 0 there, and it would fill it with zeros. However, if you tell C++ that this is an unsigned integer, then it will not do that. It will always treat the most significant number coming in with a right shift with a 0, because it will treat that as a positive number. An unsigned integer is always positive, so if you shift right, it's got to maintain its same value, so you got to pull in zeros. Something interesting to note here, when we learn, math back in grade school, we learn that anything that is a power of 10, right, is a multiple of 10, it has a 0 in the least significant digit. And we can divide by 10 just by chopping off the least significant digit. Or we multiply by 10 by just adding a 0 on the end, right? That's because we're in base 10. Binary is base 2. So adding a digit to a base 2 number is multiplying it by 2. Chopping off a bit is dividing by 2. So every time we shift, we're either multiplying or dividing by 2. And so you'll see this kind of thing happening in a couple of places. One is just bit manipulation, like you've got those flags and you want to mask out various flags, or I believe we did in an earlier lecture, we saw this with the endian swap, where we wanted to take like the most significant 8 bits and pull it down to the least significant position, and we did it with a shift. Another place you'll see it is to do divides by 2, divide by 2, divide by 4, divide by 16. You can do that with a shift. And you'll see that when you look at your compiled code, the compiler has probably noticed that. If you're multiplying by 16, you'll just see that as a left shift. You're dividing by 32, you'll see that as a right shift. All right, next up. Like the OR, we have an AND. The AND operator, just like the OR, instead of putting and, so 2 ampersands, you put 1 ampersand. 2 ampersands means logical AND. If this is true and this is true. The single ampersand says take every bit individually and do the AND operation bit by bit. So let's just look at our example here. 0 and 0 is 0. 0 and 0 is 0, 0. 1 and 1 is 1. 0 and 1 is 0. So this is false and true, so that's false. False and true is false. True and false is false. False and true is false. So we got that. You'll see this used very often when we're trying to mask some bits out. We saw that in the endian swap. And we'll see it often with these flags. You want to say, is the enable flag, or is the enable sound flag true? Does the user want sound? You'll test that by just doing the AND with your flag. So you've got your flag coming in, AND it with that. And that will come out as all zeros if that flag is not set. Or it will come out as the value enable sound. The value enable sound, whatever bit that is, will be the answer if that flag is set. So if that flag comes out as non-zero, then you know that sound is enabled. Okay, interesting little tidbit. Back to what we talked about in the previous lecture. In a 32-bit float, or a 32-bit signed integer, the most significant bit is the sign bit. So if you're trying to test whether something is negative or not, you could do this. You could say, give me the most significant bit. Right? So that's 1 shifted left by 31. So you could write that out. You could write that out. You could write it in binary or in hex or calculate what the number is and put it, or you just don't want to think about it. Just go, I just want the bit number 31. So I'll just do this, and the compiler will work that out for you. These are all constants, so it won't appear as a shift in the final compiled code. So I'll just take if this and do an AND with whatever your number is, whether it be a float or an integer, and if that comes back as 0, your number is positive. If it comes back as non-zero, your number is negative. And you'll notice here, I didn't even put the not equals 0 on the line. In C++, a Boolean, a logical value of true, is always considered to be anything non-zero. The value of 0 is false. Anything that is non-zero is logically true. Now, the shifting. Shifting, you'll see it from time to time in what we call fixed point math. And maybe I'll take a moment here to talk about that. But first, this redonkulous interview question. I don't like this kind of interview question because it's a trick question. But I've read that this type of question appears once in a while, so I want you to see it and kind of know how to approach it. And that's frankly why I don't like this as an interview question, because it's not testing your ability with C++. What it's doing is testing whether or not you've seen this trick before. So if somebody does that, let's show you the trick. How do you multiply by 640 without using star or without using any loops? Okay, how do I do that? And first of all, why would you want to do that? I can't think of any good reason to do that, other than a silly interview question. So thinking back to what we said before, shifting to the left is to multiply by a power of 2. So if this was, how do I multiply by 512? I could do that. 512 is a power of 2. So I could just shift to the left by 9 bits, and that is multiplying by 512. But that isn't 640, and 640 isn't a power of 2. So what can we do? Well, we can break 640 down into, that's 512 plus 128. Okay, so sure. Why? Well, because these are 2 powers of 2. So if I take I times 512 and I add I times 128, from the distributive property, that is I times 640, right? And so this can be done with shifting, and this can be done with shifting, and that's the trick. Okay, so that's the trick for that one, just in case it pops up. What else did I want to talk about? I wanted to talk about fixed point math really quick. This is something that I have seen coming up in interviews, in take-home tests, really. We don't use it much anymore. We used to use it all the time back before we really got floating point and floating point math processors and stuff. But you still see it in interviews, and possibly it still has relevance in trying to really compress your data format. For a floating point representation, we saw how that was 32 bits of representation, and maybe we don't need all 32 bits. maybe we don't need the value to float, right? We talked about how the float was there to give us huge dynamic range. But there's lots of numbers that we use in games that really don't need dynamic range. Consider, for example, a normal. A normal is a vector, so we'll have three floats, x, y, z, and those three floats, each individual float has a range of -1 to 1, and it can't ever get bigger than that. So we don't need large dynamic range, and we don't need incredible levels of precision to where, like, if the number is very, very close to 0, then we don't need to say how far off 0 it is. If we could just fix that range, at say it's -1 to 1, that's the whole thing, just put your fractional part in that range, then we could save ourselves some bits by doing that. And it makes sense to do that. So we might use something called fixed point math, which is different from floating point. And what that is we simply say we won't use a float, we'll use an integer, we'll use an int. So normally when we do an int, the decimal point is at the end. So let's take an 8-bit integer, right? And so 1, 2, 3, 4, 1, 2, 3, put a 1 there. That's the number 1. And then ostensibly that's the decimal point right there, right? So 1.0, right? How could we represent, let's say I want only to represent -1 to 1. So I'm going to need a sign bit. So I'm going to say this is going to be my sign bit. We'll use 2's complement. So if that bit is 1, then it'll be a negative number. If that bit is 0, it'll be a positive number. So we have 1 bit for that. That leaves us 7 more bits. Okay, let's say our maximum value is 1.0. So let's call this digit here the ones place. Instead of saying the ones place is here, that's the ones place. The 2's, the 4's, 8, 16, 32, 64. Instead of saying this is the 64's place, let's change it up. Let's say, no, this is the ones place right here. That's the ones place right there. So this is the halves place. That's the halves place there. The quarter, the 8th, 16th, 132nd place. This is the 164th place. All right, so that's what we're doing. And now all we've really done is we've said this decimal place isn't there. The decimal place is right there. Okay? So that's why we call it fixed point instead of floating point. The decimal place doesn't move up and down. The decimal place is fixed in that location. And it turns out we can just do integer math very easily with this. Let's say, for example, we want to take the value 0.5. The value 0.5, let's represent that. 0.5 equals, it's a positive, has no whole values. There's I'll put our decimal. It has 0.5, and then the rest are 0. 1, 2, 3, 1, 2, 3, 4. And let's add 0.25 to it. We'll add a quarter to that. How do we do that? We simply, let's just 0.0, and here's the quarters place. 1, 2, 3, 4. How do we add those together? Well, we just add them. 0 and 0 is 0. 0 and 0 is 0, 0, 0, and then here, boop, boop, boop. I got all crooked. Okay, 0 plus 1 is 1. 1 plus 0 is 1. And then here's our decimal place. 0 and the sign bit 0. So what number is that? That is half plus a quarter, 0.75. So addition in fixed point math is just plain addition. How about multiplication? Let's take 1.0 and we'll multiply by, I don't know, 0.5. That should be pretty easy to do. Let's do that. So 1.0 is, there's our sign bit and our ones bit. Put my decimal, 0, 0, 0, 0, 0, 0. And I'm going to multiply by 0.5. Okay, if I just multiply these as integers, what am I going to get? I'm going to get a very large number that's going to overflow my 8 bits. Let's take a look. Put it in binary, and we'll enter these numbers. 1, 0, 0, 1, 2, 3, 4, times 1, 0, 1, 2, 3, 4, equals. Okay, let's write that down. I got 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Okay, that's the number that I got by simply multiplying those, and that is not the correct answer. What was the correct answer? We should have gotten 1/2. Why didn't we? Now remember, every time you multiply the two numbers, right? Remember how we did this when we were kids and we were learning how to do this in base 10. You had to take however many of these bits, however many digits there are past the decimal, and remember to take the decimal with you, that number of digits, right? So our decimal needed to go, decimal's not here, it's 1, 2, 3, 4, 5, 6 for this one, and another 6 for this one. 1, 2, 3, 4, 5, 6. So the decimal was supposed to go there. And what we wanted is 0, 0, point the rest. But we only have 8 bits to represent that. So we want the most significant of these 8 bits right there, leaving these other bits to fall off into the too small to represent bits. How do we do that? We do that by shifting to the right by 1, 2, 3, 4, 5, 6 bits. And how do we decide that the number of shift is 6? That is the number of fractional bits. So to multiply two fixed point numbers, what you do is you're going to want to promote them to the next larger size. So if they're 8-bit numbers, promote them to 16-bit numbers, multiply them as integers, you'll get this, and then shift to the right by the number of fractional bits that they represent, and then you have the correct answer, and you'll get 0.5. You'll get this number here, which is the correct answer. And so that's multiplying. So when you see multiply, if you want to do a fixed point multiplication, first you do the multiplication, and then that'll be followed by a shift to the right to fix the decimal point. Division is similar. You're going to want to shift to the left to move that decimal point up, and then do the divide. And that's fixed point math. All right, one more operator here. Let's look at the not operator, the tilde. Like with or and, we have logical or, which is 2 pipes, but bitwise or is 1 pipe. With logical and, we have 2 ampersands, so the bitwise and is 1 ampersand. The logical not operator was the single exclamation point. So that pattern's not going to work. So they look at the keyboard and they go, well, the tilde is next to the exclamation point. So tilde is it. Tilde is the bitwise not. So we just go through each bit of our number. Zeros become ones, ones become zeros. Boom. And we've used that before. The final, the final operator I'm going to show you here is something that's pretty rarely used. It does have a legitimate application, and then I'll also show you this silly application. This is the exclusive OR. The up caret in C++ does not mean raised to the power of. Like we'll often see, you know, in other languages, x up caret 2, that means x squared. That is not what it means in C++. So watch out for that. It means exclusive OR bitwise. What is exclusive OR? 0 or 0 is 0. 0 or 0 is 0. 0 or 0 is 0. 1, exclusive OR 1 is 0. Exclusive OR means if this is true or that is true, but not both. So it's kind of like the light switch in the kitchen. When there's 2 light switches in the kitchen and either one toggles the light, right? So if you turn this one up and this one's down, the light's on. But then you flip this one up and now the light goes off, right? And then you flip this one down and it goes back on. That's an exclusive OR. Now where this comes up, and I've seen this in McDowell's Cracking the Coding Interview book. I've seen it elsewhere, I think, as well. So apparently people do sometimes still use this. An interesting little piece of trivia is that you can use the exclusive OR to swap the value of 2 variables. Like normally if you want to swap x and y, you have x, I have y, I want to swap them, I would just say z equals x, x equals y, y equals z. Done. But if for some reason you do not have one more register, like you've used every register, you don't have one more register to be the z, what can you do? You can say x equals x exclusive OR y, y equals x exclusive OR y, x equals x exclusive OR y, and what will happen is the bits will swap places. So that's sort of useful to know if you encounter that question. If you encounter the question, you don't have to remember much, just, right, it has to do with exclusive ORs, and then you could probably bang that out or just memorize it, but it's a silly question and hopefully people won't give it. Where it does come up is in leading edge tests. We've done leading edge tests for, you know, joysticks or whatever, a space bar. If the space bar was down but now is up, and if the space bar was up but now is down, that is an event. An event has occurred. So if you just want to say, hey, has an event occurred on this bit stream? You can ask that by saying, you know, here's my old bit stream, here's my new bit stream, exclusive OR them. If any of the bits have changed, I want to be notified. And so you can do that with an exclusive OR. Just have any of the bits changed. Okay, that's the end of lecture number 2 here, the bitwise operators. Join me back here on part 3 where we will get into this 3D math that I promised. Okay, see you in part 3.